we're going to use Green's theorem to find the circulation around the right lobe of this lemniscate right here. We have the equation, and we also have the vector field. Now let's try to write down Green's theorem first so we can sort of decipher what it's trying to say. So we have the integral, this f dotted with this dr, and that's going to be equal to an integral of a dx plus b dy, which could also be equal to bx minus ay over dA. And essentially, if we're trying to integrate over a closed circle, so essentially that's what we're trying to do here, and we're going to integrate the circulation. This is going to give us circulation. This is what Green's theorem says we can do. We can use one of these two versions. Now, which one of these looks somewhat familiar to what we've got over here? If I call this A and this B, then maybe I can take the partial of x on here and the partial y on here, and I can maybe try to solve that. So let's try to set up a double integral, and we're going to take the bx on this side, and that's just going to be, if I was to take the derivative of this, that would just going to be cosine x, right? It would be a negative cosine, but we'll also have this e to the y situation in there. So negative cosine x. Then we're going to subtract the ay component over here. So I think there we get a -1. And then on this side, you're just taking the derivative of that, which would be negative ey cosine x. And then we're going to use this over dA. And dA is right here. But I think we can parameterize this and say r dr d theta if we're going to do some polar coordinates. Now, if I try to solve this in here, I'm going to get like a 1. And then, isn't this just negative e to the y cosine x plus e to the y cosine x? I think that's all just going to go away. And so we're just going to try to be integrating 1 r dr d theta. Well, I think that's pretty easy. So now let's try to figure out what these things are. Well, obviously we're going to have the r expression already. We can say that r is going to be equal to the cosine of 2 theta. So we can go, r is going to go from there to the square root of cosine of 2 theta. But then the thetas might be a little bit harder. So I think we might be able to do this if we think, if we start with a theta of 0, what's going to happen to the r's? We're going to get, if I put in the 0 of cosine of 0 is 1. So 0 would give me an r of 1. We're going to start here. And if I want to follow this around and actually get over here, and I'm looking for a 0 for the r. If I can somehow get an r of 0, then maybe I'll figure out what that theta would be. How do I get an r of 0? This stuff has to equal to 0. How do I get cosine 2 theta equals 0? I think if I had a theta of pi over 4, then that would successfully turn the cosine of pi over 2, which would give me a 0. So I think that's the theta we're going to use. And that's only giving us this half right here, so we're going to kind of want to multiply this whole thing by 2. So we'll be able to go from 0 to pi over 4 and multiply that by 2. So let's try to integrate this. It's just going to be r squared over 2. We're going from 0 to the square root of cosine of 2 theta. Obviously, that's just going to turn out to be the cosine of 2 theta. And we're also going to divide that by a half there. Then we're going to have to integrate over the thetas. So there's also a 2 that we have to add in there. So like these things are just going to cancel out. But we're going to integrate this over theta, and it's going to go from 0 to pi over 4. The integral of cosine is going to be sine. And then we're also going to have to divide that by a half. And then we just go from 0 to pi over 4. And sine of pi over 2 is 1. So we essentially just get 1 minus 0 in there. And the answer to everything is just going to be a half. Nice.